So this is a work that Anne Garnier at Analytical Mechanics Associates, it's a new name. She was at Science Systems Applications, and she still is. Basically, they just changed their name. We started pursuing this about 2 years ago, and basically this topic is first satellite retrieval. It's improvements over the one that we had before. And so I'll talk about that, how that was developed, and then go into the results of the retrieval. And Anne was responsible for a lot of the discoveries here because of her curiosity. It was really great working with her. None of this could be done without her. So what this is showing here is two types of cirrus clouds, which we'll go into detail on how that was done. But basically, you can see like the more optically thick cirrus is associated with homogeneous ice nucleation more. These are wave clouds over the Sierra Nevada, the Carson Range, actually. And then the more diffuse transparent type clouds are the heterogeneous cirrus. And I'll go into the details on all this. So the retrieval itself, we needed something that would be sensitive to the number concentration of ice crystals, especially the small ice crystals, because they comprise the highest proportion of the number concentration. You can see that on this right panel. It's from Cotton et al. 2013, where number concentration versus size is plotted. And less than 100 micron, you have this this large modality that's based on these other probes that are designed to avoid ice particle shattering, and all the data was processed to eliminate shattering. So this is a real thing, and all the probes seem to agree pretty well there. So how do we do remote sensing on that? Well, you need something that'll be sensitive to those high number concentrations that are small sizes. And this absorption process called wave resonance or photon tunneling, take your pick, it does absorb at those small particle sizes. And shown on the left side is the absorption efficiency from tunneling versus particle size for hexagonal columns. Wavelength is at 12 microns. If we repeated that at 10.6 microns, this curve would be much lower. So this absorption optical depth ratio, beta effective here, it's the ratio of the absorption efficiency at 12 microns to 10.6. And because tunneling doesn't happen as much at 10.6, you get a ratio there. And that is a measure of the small crystal concentration. So this retrieval exploits that. And this ratio is retrieved with the infrared imaging radiometer on board Calypso for single layer semi-transparent ice clouds. So here's the retrieval equations. The number concentration, we made a change in that compared to the previous version that was published in ACP 2018. So this new version is using the area of the size distribution, which is directly measured by the probes. So it's the projected area of the size distribution. And this ratio N over A is obtained from in situ data, aircraft data. And I'll go into that later, but that's how we get it, is from field campaigns. And we improve the ice water content estimation, and I'll go into that more later. We also improved the equation for the effective diameter. It's now based on theory, which this equation is basically justified theoretically in Mitchell 2002. And if we expand the terms here, so now we're using N over A times ice water content over n. The n's cancel essentially, and these are retrieved as a function of this beta parameter. So the n's cancel and you get ice water content over A. So it's the same principle. And then from the ice water content, from the effective diameter, we can get the ice water content. And the extinction coefficient for visible shortwave radiation is given on the right side here. That's a function of absorption optical depth. And this delta Z, which also occurs in the number concentration equation, that's from the Calliope LiDAR. And it's the equivalent thickness, geometrical thickness of the Cirrus cloud. And there's more details than that can be read up upon. So in essence, these ratios are these relationships of n over A related to the absorption optical depth ratio, beta, and n over ice water content, beta, and 1 over Q absorption. This is the absorption efficiency. Those are all related or based on several field campaigns, similar to the methodology in Mitchell et al. 2018. So here are the other two improvements. We use more field campaigns in the tropics, basically, and it accounts for changes in ice particles size distribution shape between the tropical tropopause layer and the lower Cirrus. So I think some articles have mentioned this in the past. I know one by Blas Gasparini in 2017 talked about how above a certain layer, you have tropical TTL Cirrus, and then more anvil Cirrus below that. So we had to account for that. And the last improvement was that we're using a new version of the Calypso products, 4.2 level 2 products. So for the masses, we're using the Irfani-Mitchell mass relationships, and they're compared here against some other recent studies. Lawson 2019 is one of them, the black curve, and it's a power law relationship, so it overestimates the large particle sizes, I would say, but it does a good job for the small crystals, and that's the hard part to get. So between 10 and 100 microns, it's pretty dicey getting trustable masses there. There's a recent study by Witzel et al. In 2020 ACP, where it was a laboratory study, and that's shown by this dotted line between 10 and 100 microns. And even though the slope's a little off, maybe, it does agree pretty well with these other relationships, Irfani, Mitchell, and Lawson, and Mitchell 2010. So we have more confidence on the small crystals, and we went with that. So when we actually put that into the retrievals, this is a comparison between in situ calculations of this beta parameter. The red triangles are the calculations based on in situ data or size distribution data, and the black curves are retrieved from Calypso. And on the left side is using Irfani Mitchell 2016 mass relationships. On the right side, it's spec standard relationships, Baker Lawson, actually 2006. And that relationship goes non-physical when the size maximum dimensions less than 47 microns. So we know that can't be true. We can't trust it there. So that seems to be why the black curve doesn't agree as well with the red triangles in the spec relationships for the smaller or the colder temperatures, which are associated with smaller or more narrow size distributions, smaller crystals. Similar for Poseidon, there's sort of an underestimation, but it seems to be much better agreement when the Irfani-Mitchell relationships at these small crystal sizes are used. So that's the improvement that we think is for mass. And then the other key points are we're only sampling single layer cirrus clouds that are semi-transparent to the calliope LiDAR. And most of the clouds sampled have a visible optical depth less than 3. And the retrieved cloud properties from the Calypso infrared imaging radiometer correspond to cloud layers and not cloud profiles. So larger uncertainties are associated with these smaller optical depths, but over ocean, it's not so bad. So we're using that over ocean. These anyway, sampled clouds have a radiative temperature less than or equal to 235 Kelvin. That's our definition basically of cirrus clouds. And number 5, these beta relationships for the microphysical ratios here, they were developed from size distribution measurements from several field campaigns like Spartacus, Atrix, and Poseidon, and using the same methodology as in Mitchell et al. 2018. And this is all of this is based on 4 years of Calypso data. And we also found from the Atrix and Poseidon campaigns that they compared the 2DS probe, which is commonly used, with the cloud droplet probe. Let's see, it's the fast cloud droplet probe, FDC. Anyway, there's this overlap region in red here and blue. And that was surprising because I didn't think it would merge so well. It was like this in about 90% of the data. So in the past, we had thrown out the first bin of the 2DS probe, but we don't see any need for doing that after looking at this data for both campaigns. We had good overlap between the probes there. So it looks like the first probe of the 2DS is realistic. So that was our assumption with Spartacus as well. And then this is what the retrievals relationships look like. N over ice water content on the upper left side. And that's kind of ubiquitous for all the campaigns here. It's like a universal relationship almost, except when you get to the lower values of this beta parameter, then it separates out a little bit for the tropics. And the mid-latitudes seem to be a little different. But anyway, yeah, we have mid-latitudes for Spartacus and also synoptic Cirrus in Spartacus in the blue and Atrix Poseidons in black. Then we can look at the area, N over area, and that's very similar to the N over ice water content, but a little bit more scatter in the data. And then we have effective diameter. And this is where the challenge came in trying to do the tropics, because there's these TTL cirrus that are the black squares. And then there's this cirrus from Anvil Cirrus associated with TC4 campaign here. And it's a little different. So we needed to do a temperature interpolation for that. Anyway, these other curves are kind of self-explanatory. So we wanted more data because we only had, for the Anvil warmer cirrus clouds in the tropics, TC4 campaign doesn't have a whole lot of size distributions. So the CPEX campaign, we went to that. I think that was in 1993. And even though they didn't correct for shattering, they have the fits for exponential. They were all pretty much like this. I did this work a long time ago. It's published in this ARM science team meeting proceedings from 1999. And they were all exponential except for the smallest bin. So we ignored the smallest bin and say, yeah, we could probably trust an exponential relationship for all the sizes. And that's how we came up with these other gray curves on the right side here is the CPEX data, where we use this size distribution scheme in this paper just for the large particle mode, which is the exponential. And it didn't fit the other campaigns when you look at these large values of beta. So we threw that part out, and we just used the smaller one beta values of 1.1 and smaller for the retrieval, to incorporate into the retrieval. So when you do that, you get these curves here, and these are not showing the data now, but it's just showing the relationships. And you can see how in the effective diameter, the gray curve for CPEX data, there's a slight discontinuity with the TC4, but it's not too bad. And the same, there's not much discontinuity at all with the other ratios, the N over A and N over ice sweater content. And a little bit more discontinuity with the 1 over absorption efficiency, but that was, if you look at the scale here, it's still not so bad. So the way we dealt with the tropics is a temperature interpolation, a new strategy to combine empirical relationships from various campaigns. So on the top, the less than or equal to minus 65 is the TTL Cirrus, and warmer than that is the anvil Cirrus that the CPEX data was used for. And the TC4 is for these 3 different relationships shown here. So outside the tropics, we use Spartacus, and we also used, if it's colder than minus 60, then we do an interpolation, but there's not too much data outside the tropics that is colder than that in terms of the number of pixels sampled. So we have, this is our basic temperature interpolation here, where X could be any interpolated quantity, any of these relationships like N over area and N over ice sweater content. And then we have a cold value based on Atrx Poseidon relationships, and a warm value based on the CPEX TC4 relationships. And we interpolate between those 2 extremes. And so those extremes would be at minus 65 and between minus 60 and minus 65. That's where we interpolate. And there is actually some microphysical evidence for this. This is a paper by Heimsfield et al. 2014, where they are looking at effective diameter versus temperature. And they also see sort of a discontinuity between the anvil Cirrus on the right side and the TTL Cirrus on the left side here at minus 80. They're getting to very cold temperatures there. So we're interpolating between minus 60 and minus 65. And that's shown by the dashed red dashes there. And that's right where they see this discontinuity occurring. And you can see it in our data too. So we retrieve a median effective diameter versus temperature on the left sides here for oceans and over land. And the dashed red vertical lines are showing where this discontinuity, or not discontinuity, but interpolation occurs. That's our temperature interpolation there. So then we compare with Atrx and Poseidon. So the Calypso, I'll just talk about the retrievals effect. Let's see, the ice water content is shown in the lower left panel, and the black curve is the retrieved curve showing the percentiles 25 and 75%. And the red diamonds are the in situ data from the aircraft, where we calculate the ice water content. And the similar thing for number concentration is shown here. And also for effective diameter on the upper right panel. So I think the agreement seemed reasonable with those. And then the Poseidon data is on the right side. And for ice water content, there's reasonable agreement, except there's a difference at the warmer temperatures there. For the number concentration, that seemed pretty much, down the middle. And then effective diameter is also reasonable. So then we compared with Spartacus data, and we found the ice water content was reasonable. For effective diameter and number concentration, there's at the very coldest temperature, it's ridge-crest cirrus clouds. Those are more like orographic gravity wave cirrus that produce high number concentrations, small sizes. So it makes sense that this would be a little lower than the retrieval is looking at. So the retrieval is over a 6-month period. It's sampling a lot of clouds that are not sampled by aircraft, of course. So it's not expected to be a perfect comparison. So the retrieval is just based on the same time period in the same region that Spartacus occurred over. And the same is true for Atrex and Poseidon. And here's number concentration, and that looked reasonable. So, of course, these are a little higher at the end there at 210. So we also had to compare with Martina-Kramer's climatology, and that's shown by the black curves here. And we have the RV is the volume, the mass volume radius. It's essentially ice water content over number concentration times a constant. And we have, the comparison here is, okay, so we have for all the optical depths that we could sample over ocean, which is 0.005 actually to 3. Those are shown by the blue curves. And there's less agreement with the in situ climatology when the optical depth range is less, like between 0.3 and 3. So that's where you have the lowest uncertainty in your retrievals, but it's not representative of all the cirrus clouds. And here are the percentiles used. Anyway, number concentration is, if we compare the blue for all the latitudes relevant to the climatology, it agrees within 25 percentile. So I thought that was reasonable. But when we look at like the red curve, that's only for the optically thicker cirrus, 0.3 to 3 optical thickness. There's less agreement. So that was interesting. And then ice water content, again, when we use all the optical depth that we could retrieve, 0.005 to 3, we get pretty good agreement there, but less agreement when the clouds are optically thicker. So that motivated us to compare, to explore this issue a little deeper. So the Calypso retrievals are shown here for the thicker optical depths on the left side, and the thin optical, or the greater range in optical depth, on the right side. And the black curve, that's a smooth curve, is from Schiller. That's a median ice water content that's bisecting all of the data. So that's the median value from Schiller. And on the left side, when we're using the thick optical clouds, we get pretty good agreement with the Schiller data. So it makes me wonder, if the Schiller data was flying in optically thicker clouds, and then on the right side, Martina-Kramer's data, the blue here is is based on all the optical thicknesses that we can sample. And then we have pretty good agreement there. So there's a little bit of uncertainty, it seems. When you're comparing with in situ data, you want to know what type of clouds were sampled, if they're optically thicker or not. And then for liquid, we also wanted to differentiate between liquid origin and in situ cirrus. So the way we did that was for a column of atmosphere. We defined a column of atmosphere in terms of the cirrus layer radiative temperature and the cloud base temperature. For the in situ cirrus, TR and TB are both less than or equal to 235 Kelvin, which is our definition of cirrus. While for the liquid origin, TR was always less than or equal to 235, but cloud base temperature could be more, was always more than that. It had to be more than that. So that means that some of the condensate from below, it could be liquid, and then freezing as it crosses that isotherm. So when you retrieve the clouds that way, this is what you get. This is an example of for retrievals over ocean. This is the in situ fraction using all the samples, all optical depths for December, January, February, and July, June, August on the right. But basically there's a transition that occurred around 225 Kelvin. And that's fairly consistent with the other studies we looked at, like the Cirrus and Anna Lubke's paper in 2016, I think. And you can ignore these black lines for now. That's something I'll go into later. So here we are exploring, how do we find out if a cloud is having homogeneous ice nucleation? And we looked at optical depth less than 0.3 and greater than 0.3 on the left and the right here. And this is number concentration plotted in TR versus TR minus T-top space. So TR is the radiative temperature, T-top is the cloud top temperature, and the difference is related to the cloud geometric thickness, because TR is most of the time near the middle of the cloud. So you can look at this x-axis as a measure of geometrical thickness of the cirrus cloud. And when the clouds are relatively thin, we have high number concentrations, that like around 500 per liter at times. So when the cloud's much thicker, the concentration drops off a lot. This is very similar to the Spitztinger and Gearin's paper in 2009. It's part A and B they published, and they had very similar results in their paper. It's a modeling paper. On the low optical depth side, we don't see this structure showing up hardly at all. So the thin clouds there are a little bit higher in concentration, but in some cases, but not so much. So that seems more characteristic of heterogeneous nucleation on the left side, where thin cirrus on the right are more like homogeneously nucleated. And when we look at ice water content, we see the same type of thing. The ice water content on the right side is much higher, especially for the thin cirrus clouds and the warmer cirrus clouds. So that's more characteristic of homogeneous ice nucleation. On the left side, it's more like heterogeneous nucleation rules the day there. So you don't see that feature as much. For effective diameter, we don't see too much difference between what I would say is the heterogeneously dominated optical depth region and the homogeneous type cirrus. This is only over oceans, though. And we could say that when homogeneous ice nucleation is relatively active based on the high and in ice water content. Um, um, it's when it's active over land, the effective diameter decreases. So looking for a parameter to describe this transition between the heterogeneous and homogeneous cirrus clouds, we came up with the extinction coefficient, which is expressed as basically ice water content over the effective diameter times a constant. So extinction seems to be a good parameter to try to separate out these two regimes for homo and heterogeneous ice nucleation. So we plotted number concentration in temperature versus extinction space to investigate that. And you can see that these are different regions. So winter is WIN and summer is SUM. Ocean, mid is for mid latitudes, tropics on the left, and high latitudes on the right. So in all cases, they separate out where you have this region of light blue, which is more typical of heterogeneous ice nucleation with concentration. The blue is concentrations less than about 50 per liter. So there's this gradient. We think this gradient in concentration is due to homogeneous ice nucleation, where on the far right side, you're getting thousands per liter in concentration. So to explain this, we went to the Clausius-Clapeyron equation. We wanted to know, this is an interesting diagonal thing going on here on the right side. How do you explain this, or the whole gradient for that matter? It's this diagonal orientation. We wanted to know what that's about. So we checked out the Clausius-Clapeyron equation, and we came up with an expression for the ice water content due to homogeneous ice nucleation, shown at the bottom here. And the way we got that is look at the supersaturation where homogeneous ice nucleation occurs, given by this equation, SI, and then look at the saturation where it's just ice saturation. And you take the difference of those two, and you get an approximate value anyway for the ice water content. So that would occur for homogeneous ice nucleation at the time of nucleation. So we plot this. We also can calculate the effective diameter and the number concentration from that. And to do that, to get the effective diameter, for the tropics, we used the CPEX relationship for for mean particle size. So shown in this plot on the left is the slope parameter. To get the mean size, it's just 1 over lambda, the slope. And then for the mid-latitudes, we use the Spartacus field data. And this is a plot of the mean size distribution dimension versus temperature. And it shows here how the mean maximum dimension of the size distributions were related to the d mean was converted to the effective diameter for exponential size distributions using the particle mass and projected area dimensional relationships from Irfani and Mitchell paper. And then less than 235K effective size was reduced by a factor of 0.636 based on the impact of homogeneous nucleation on effective diameter that was deduced from the retrievals we had. So from these retrievals, we could see how much that effective size was being modified by homogeneous nucleation. That was just over land, mostly, that happened. And for number concentration, we use this equation. The slope parameter here is also for homogeneous nucleation. And the ice water content is too. And the alpha beta values are from these mass dimension relationships, and we got those from Irfani and Mitchell. So when it's all said and done, this is what we get. is a relationship. The triangles are the calculated values for number concentration in the upper left panels. And this is for over oceans, all samples on the left side. On the right side, it's for optical depths greater than 0.3. And that had to be done because effective diameter couldn't be retrieved. We couldn't trust the values for the lower optical depths. And ice water content is calculated from effective diameter. So that's why we restricted the optical depth on the right side. On the left side, we could use all the optical depths. And you can see that the triangles have a color inside, and that's based on this legend at the top. Same legend the satellite data is based on. So in the background, satellite data has the same color as the triangles. That indicates agreement between theory and the satellite retrieval. And basically outside the tropics, we get pretty good agreement in the number concentrations. And the same with the effective diameters that we're looking at. The colors match up pretty well. And the best agreement was with the ice water contents. They all agreed pretty well with the retrievals. So what shows on the lower left panel is the frequency, the occurrence frequency, or the sampling density, you could say. The predicted homogeneous nucleation for pure homogeneous nucleation is the black triangles. So similar to what we have in the other plots. But now you're looking at the sampling density. So it's expected that homogeneous nucleation is a very rare event. It doesn't happen very frequently. So it also shows the same thing here, that it's associated with very few of the samples. In the tropics, it's a little more. But on the other hand, in the tropics, the number concentration doesn't agree with the satellite retrievals very well. So there may be in the tropics, homogeneous nucleation is not so important. So the way we went about trying to investigate the fraction of cirrus clouds that were strongly affected or impacted by homogeneous nucleation is by plotting the effective diameter against the extinction coefficient. When there's a maximum, the vertical dashed line here corresponds to the temperature bin at the kind of the dark pink color. And that just illustrates how we separated the two regimes, the Het and the Home regime. So on the left side of the maximum for a given temperature interval, like a 4-degree temperature interval, to the left side is the heterogeneous regime, and the right side, that's the homogeneous regime. That's a more conservative treatment of the approach of defining these two regimes, because it ensures that the microphysics is very different between the two. So when you do this on the lower panels here, it shows the plus marks are showing how we, for a given temperature, how the regimes separate. So for each temperature interval, we have a effective diameter maximum, and that's indicated by the plus marks. When the maximums disappear, we can't see any maximum any longer, then we draw this horizontal dashed line. And so anything above that horizontal dashed line is no longer showing evidence of homogeneous nucleation. So that region that's bounded by the plus on the horizontal line is the homogeneous region. So all the samples or the pixels in that region are considered homogeneous cirrus clouds, or strongly home-affected cirrus clouds. And we can also plot, when we do that, we can get this result here. The number of samples are shown in the upper panels. They're normalized to unity. And then the lower panels are showing the actual fraction of homogeneous affected cirrus clouds, which I'll just call it home cirrus for short. And you can see that in the wintertime, there's more home cirrus than there is in the summertime. And it depends a little on what months you're looking at. So December, January, February on the left, and June, July, August on the right. A lot of home cirrus along the coast of Antarctica, which will become more apparent here. So this is showing the home fraction again, and it's seasonal. So December, January, February on the left, and June, July, August on the right. So wintertime in the southern hemisphere, you're having a lot of home cirrus clouds. When we look at the dust concentrations, we find that there's a strong contribution of Asian dust, like from Mongolian, the Gobi Desert and the Taklamakan Desert. That's what is referred to here by Asia. And during June, July, August, most of it is due to that. So it's basically the Asian dust is comprising about 60 to 70% of North American dust in the atmosphere. And so, it's a strong contribution during the summer in North America. In the southern hemisphere, the dust is coming from South America, mostly in the wintertime. And then in the summertime, it's both South America and Australia. So down here, this is a paper from Koch et al. 2021, where South America, you can see between winter and summer, there's about a doubling of dust optical depth, the dust aerosol optical depth. And then in Australia, it's even more of a change between winter and summer. So when you look at the downwind regions of these dust sources in December, January, we'll start with the northern hemisphere. There's a lot of home cirrus to the right of that red arrow. Yeah. So the red arrow is over those dust sources, and downwind of it is Pacific Ocean. There's a lot of home cirrus. But then in the summertime, when the dust concentrations increase, it goes away to a great extent. So there's a climate intervention idea called cirrus cloud thinning, or CCT. And this seems to be a natural analog to that. Like, we don't have the actual dust, all the details here, but based on those previous studies by Freud et al. And Koch et al., it does seem like something like that might be occurring. And same with the southern hemisphere, there's about at least a doubling of dust aerosol optical depth, probably more than that, between seasons. So when there's less dust, you have more home cirrus in the Southern Ocean region, and a lot less home cirrus in the Southern Ocean when you have more dust. And then we also looked at the zonal means for the cirrus fractions. So between outside the tropics, in the tropics, we don't see a whole lot of home cirrus, but outside the tropics, we do, more anyway. And it's basically between 20 and 35% outside the tropics, with the exception of Antarctica, where it can get quite high. Also, we can multiply the fraction of home cirrus by the corresponding optical thickness. And when you do that, when you weight it by optical thickness, you get these bottom panels here. And that is showing sort of a proxy for the cloud radiative effect. We did look at cloud radiative effect calculations from Hong and Liu paper 2015, and it did seem to correspond pretty well with that. So I think that's a reasonable way of looking at it. It's certainly related to the cloud radiative effect when you multiply it by the optical depth. So it's more than 50% outside the tropics. So the bottom line is that we think these home cirrus clouds are making a substantial contribution to the Earth's radiation budget. And this figure was suggested to me by Martina Kramer, and it shows that what's shown here are the black triangles, which are the similar to the plus marks before. They are the transition between the het regime and the home regime. And the navy blue curve is the median ice water content. And these are just showing different latitude zones and different seasons around the world. With the exception of this plot, in which case we didn't have a very strong, hardly any contribution at all of home cirrus clouds. So I'm not too concerned about this particular plot here, but all the other plots show a pretty good correlation or a similarity where the transition occurs near the median ice water content. So that was an interesting finding. So this last topic this is the last topic, where the maximum in effective diameter occurs, there's also a maximum in the geometrical thickness of the cloud, which is represented by TR minus T top, the radiative temperature minus the cloud top temperature. So that's a measure of the geometrical thickness. And that maximum is occurring in the same place at the same extinction that the effective diameter maximum occurs at. So we postulate, excuse me, we postulate these matching maxima are not a coincidence, but rather they point to an underlying process. And this is the process that I think they point to. Shown here are like kind of a cartoon of cirrus clouds, where we have cloud base shown by the virga at the bottom and cloud top at the blue horizontal line. And as we have the arrows are showing the updraft, so it's a steadily increasing updraft with ice water content. And there are papers in the literature that'll show you that as the updraft increases, the ice water content increases too. So they're both increasing with from left to right. And we're going from heterogeneous cirrus clouds into a homogeneous regime. And there's a transition right around the median ice water content. So that previous plot is relevant here. This is around the median ice water content in the middle. And that's where you get this transition from het to home. So the reason that the clouds are becoming deeper, we think, is because there's more sedimentation, more virga, more export of condensate to the subcloud layer. So we're moistening the subcloud layer that allows the cloud base to descend, basically. And the bigger the crystals become, which we observe from the retrievals, the more virga we get and the more moistening of the subcloud layer. So your maximum thickness occurs around the median ice water content. And then you start moving, as you increase ice water content even more, or the updraft even more, you're getting homogeneous nucleation more and more. And that's creating smaller crystals. And these smaller crystals are sedimenting less and less because their fall speeds are lower. So it's really driven by the fall velocities of the ice crystals that they are the homogeneous nucleations making them smaller and they're less sedimentation. So when you get these really narrow or thin cirrus clouds, that's when you see the highest number concentrations. And they're thin because they have the lowest sedimentation rate. So that's our hypothetical understanding of this. And that's kind of similar to what Martina Kramer has in this revised figure from her figure 9 of a previous paper, where she also shows like a median ice water content that separates the heterogeneous from the homogeneous preferred freezing. So on the bottom here, it says preferably het freezing, fewer ice crystals, and preferably home freezing above the median ice water content. So it's the same idea, more or less, and higher updraft and lower updraft. And finally, this is just what these clouds look like. On the left side, we see the typical heterogeneously nucleated cirrus clouds. And on the right side, this is associated with a warm front moving over Lake Tahoe in the central Sierra Nevada mountains. And you can see the sun, you can see contrails going through there. So it's not as thick as it might appear, but it is, it's probably having an optical thickness of 0.5 or something. When the sun disappears, there's an optical thickness of 1. So that's one example, but the main point I wanted to emphasize is here's an example of wave cloud, homogeneous cirrus clouds, home dominated for sure. And they cover a big extent. So this is a satellite picture taken 10 minutes before that picture was taken and 10 minutes before or after. Anyway, they're fairly optically thick and they cover an extensive area. So it may not be as narrow an area as you thought. So I think I've already covered these. We're running out of time, I think. So I'll just leave these up here and take any questions people have.
Thank you, David.